Now let's look at protecting groups. There are sometimes we run our reactions and we want a nucleophile, a strong nucleophile, such as organometallic reagents. We want them to attack the carbonyl. However, there's a hydrogen on the atom, or excuse me, on the molecule that's on an oxygen atom or a nitrogen atom that's fairly acidic. And so a strong nucleophile is always a strong base because nucleophilicity parallels basicity. Well, usually, there are those exceptions, but usually a strong nucleophile is a strong base. So the strong base, the nucleophile, would rather take a hydrogen off an oxygen or nitrogen than attack a carbonyl. The hydrogens are always on the outside of the molecule. Carbons are buried in underneath those hydrogens. So if a carbonyl compound has OHs or NHs, organometallic reagent will act as a base and take that hydrogen and not attack the carbonyl carbon. It won't act as a nucleophile. Here's an example. We've got this ketone here that's got an OH at the end. You want the Grignard reagent to add here, but it's not. It's just going to take this hydrogen, giving you this, and then everything is sad. As we said before, what can you never have if you're doing organometallic reactions? Can't have alcohols around because they kill it. And if your alcohol is part of your molecule, it'll kill it. So what do we do about this situation? We're going to convert the OH, we're going to convert the alcohol into a different group using a protecting group. Once we do the organometallic reaction, when this group is protected, we're going to deprotect it, change it back to the OH. So we need a way to fairly easily change this group, the alcohol group, into a group that's non-reactive, do organometallic reaction, then change it back to the alcohol. There are multiple ways we're going to be looking at, and the first one is with tert-butyl dimethylsilyl ROTBDMS in ether. Okay, or here's the deal. We're going to use this tert-butyl dimethylsilyl TBDMSCl. And that will change our ROH, our alcohol. We add here, here's our tert-butyl dimethylsilyl. With this imidazole, this weak sterically hindered base imidazole here, it will change this into ROTBDMS. And this is a silyl ether, ROSI. Recall that silicon is right under carbon on the periodic table, so it has similar reactions to carbon, wants 4 bonds, etc. And so we call a carbon-oxygen-silicon group a silyl ether. The most important thing is that hydrogen is gone. We have converted that alcohol to that silyl ether. And so now the alcohol is unreactive. And the nice thing is when you have that silyl ether, you can convert it back to an alcohol with a quaternary ammonium fluoride compound. So tetrabutyl ammonium fluoride, 4 butyl groups on a nitrogen gives that nitrogen positive charge, F minus will work. Sodium fluoride, NaF, will work for this if your reaction allows the sodium fluoride, fairly ionic compound there, to get close. If your solvent will dissolve that sodium fluoride. So sodium fluoride will work, tetrabutyl ammonium fluoride will work, and it will convert this silyl ether, using some water from the previous step, back into the alcohol and put a fluorine where that chlorine is to be on the silicon. So here's a nice little scheme here. Here's our starting molecule. We want to add a methyl group to the carbonyl carbon. That's what we want, is a methyl group on that carbonyl carbon. But we see this OH here, so we know that the nice way to get methyl groups on carbonyl is organometallic reagents, but they will get killed by this alcohol. So we protect the alcohol with TDMSCl and imidazole, makes our silyl ether. Then we put in our Grignard reagent here, our organometallic, which we realize will put this methyl group on the carbonyl carbon. becomes an alkoxide. Aqueous work up here protonates that alkoxide. And now we have an OH and a methyl group on that, another methyl group on the carbon, formerly known as carbonyl carbon. But we've got the silyl ether here. Our fluoride compound changes it back to the alcohol. So protect the alcohol, run the organometallic reagent, deprotect the alcohol. We've got our alcohol back, and we've got our methyl group on that carbonyl carbon. Yay, the peasants rejoice. All right, so now we've been looking so far at what happens when we're adding organometallic reagents to aldehydes and ketones. Recall the carbonyl carbon of aldehyde and ketone is bonded to another carbon, strong carbon-carbon bond, or it's bonded in the case of the aldehyde to a hydrogen, fairly nonpolar, fairly strong carbon-hydrogen bond, no leaving group. Now let's look at RCOZ compounds where we're going to have a leaving group on our molecule. So, for example, if we have an acid chloride, acyl chloride, or an ester will do the same thing. You react it with a strong base. Recall, organometallic reagents react as carbanions. Carbanions are extremely strong bases. It turns out you'll have to add 2 equivalents of your Grignard or your alkyl lithium, followed by water later, and we are going to get 2 ethyl groups. Note, let's track our atoms here, our atom economy. We've got this CH3 here. Okay, here it is here. Our carbonyl becomes COH. The chloride isn't there anymore, and we've got 2 ethyl groups from the Grignard reagent. I think we can see if we were to look at the mechanism. I bet you, hopefully you can imagine and say, okay, what's the first thing that's going to happen? Well, this carbon, acting as a carbanion, will attack the carbonyl carbon. Double bond breaks, the pi bond breaks. The pi bond reforms and kicks off the chloride. And so that will reform the carbonyl and have this ethyl group on there. But we've got an we've got our Grignard here, or alkyl lithium here, and we've still got a carbonyl. It will attack again. A second equivalent of organometallic will attack the new carbonyl and make that tertiary alcohol. And that's the deal. With acid chlorides and esters, we always form a tertiary alcohol when you use Grignards and organometallic reagents. It does not stop at the ketone, because Grignards and organolithiums are just too powerful. When you have the leaving group here with ester or an acid chloride, the first Grignard or alkyl lithium reagent does a nucleophilic acyl substitution to turn it into a ketone, but then we know that Grignards and alkyl lithiums will attack ketones just fine, and so you have to put in that second equivalent. Nope, you can't just stop. If you only put in one equivalent of your Grignard reagent, if we only put in one equivalent, we'll get a mess, because some of the Grignard reagent will attack this carbonyl and do the substitution to get our ester, or to get our ketone here with the ethyl group on here. And now, sitting in solution, you have some unreacted starting material. You have some of the ketone in there, and you still have some of this reagent in there, and so some of this will attack the ketone, some of it will attack this. You'll end up with a mixture of unreacted starting material, the ketone, and the tertiary alcohol all mixed in there together, and it's just a mess. So you really do have to add the 2 equivalents. There's no way to stop it from going to the ketone. Of course, you say, but I want to stop at the ketone. I don't want to make a tertiary alcohol if I have an acid chloride or an ester. Good news. If you use organocuprates, R prime to CuLi, organocuprate molecule, with an acid chloride or an ester, they stop at the ketone. If you add one equivalent of your organocuprate, it will stop at the ketone. So that's how we do it. Stopping at the ketone with organocuprates, tertiary alcohol with Grignards and alkyl lithiums. Cool. More stuff, some interesting stuff when we're dealing with these organometallic reactions here. If you take a Grignard reagent or an alkyl lithium and add just carbon dioxide, literally you throw dry ice into it. You make your Grignard reagent and you throw in dry ice, solid carbon dioxide, let the reaction run, do water or work up with aqueous acid, you will make a carboxylic acid. All right. Note that this carbon of carbon dioxide is now part of your molecule. We have increased the carbon chain of our molecule by one carbon. For example, if you started out with CH3 MgBr and you added CO2 in the first reaction, followed by H2O in the second reaction, we will now have CH3 C double bond O OH. We only had one carbon in our chain as our reactant. Now we have two carbons, a CH3 and a carbonyl carbon. And you're saying, yeah, but oh, big deal, we've got a carbonyl carbon on there, but we throw in some lithium aluminum hydride, and we've reduced that to a primary alcohol. So now we have a 2-carbon primary alcohol. Ooh, take that 2-carbon primary alcohol and let's look at this. This is fun. What if we did this? CH3 Br, throw in solid Mg in ether. That will give us CH3 MgBr, our Grignard reagent. Throw in carbon dioxide followed by aqueous acid workup. That will make the acid, acetic acid. But what if we followed that with lithium aluminum hydride followed by aqueous workup? That would give us CH3 CH2Br. Note, compared to where we started with, we've added one CH2. We've added a carbon to our chain. Alkyl bromide with one more carbon. So heck, couldn't we just, with this one, throw in some magnesium, add CO2, add some acid, add some lithium aluminum hydride, LaH, add some water. What would we have if we did all of this? I hope you can see. We would put another CH2. This is our alcohol, 6. Add some PBr3. I hope you can see that this will add another CH2 and put a bromine. Oh, that's a problem. I missed that step up here. This right here doesn't make the bromine. This makes the alcohol, OH. And we have to add PBr3 to convert that alcohol to the bromine. All right, cool. So yeah, this is fun. So always have to watch out. Always check your work. Go back. You find out you made a mistake. You skip a step. So methyl bromide, put in magnesium and ether, makes the methyl magnesium bromide Grignard reagent. Carbon dioxide and acid turns it into carboxylic acid. Lithium aluminum hydride, H4, and water turns it into the primary alcohol. PBr3 takes a primary alcohol, changes it to the alkyl bromide. If we then run it again with magnesium, CO2, H3O plus, lithium aluminum hydride, water, and PBr3, we add another CH2 in there. Note, this is a whole lot of work. This is not the preferred way to get to this compound. Building one carbon at a time is just forever. Let's look at this. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a lot of reactions there just to add a couple carbons. There are better ways. But if you just need to add one carbon to an end of a chain, this is one way to do it. Cool. All right. So that's nice with our carbonyl stuff here. Carbon dioxide, fairly useful for adding one carbon to your chain and taken to the carboxylic acid. Of course, we could have reacted the carboxylic acid with phenyl chloride, SOCl2, and that would have changed this to an acid chloride, which is very reactive. Could do lots of stuff with it. Another thing, going back to the fun days of Organic 1, what if we had an epoxide, an unsymmetrical epoxide? Recall with unsymmetrical epoxides, strong bases attack the less sterically hindered, the less substituted carbon. Grignards, alkylithiums, organocuprates, very strong bases, they will attack the less substituted carbon in an SN2 fashion, break off that oxygen, protonate it, and you can put this ethyl group on the less sterically hindered carbon. That's another reaction that these organometallic reagents can do. All right, so we'll end this video here for now, and in the next one, we'll look at alpha beta unsaturated carbonyl compounds, what's up with them, and how do organometallic reagents react with them.